So we have a worksheet exercise, which is the task number 2 on the worksheet. And consider the population regression line, y equals this. So these are the parameters, and they are not observable, okay? These are population parameters, the betas. And you know that, well, you are given the fact that the relationship between y and x is linear. So the figure below shows data from a sample of 250 observations of x and y. So here in the figure you have observations, these dots, and which of these lines, the solid line or the dashed line, would you feel represents the data in a better way? Because here one of the lines is the sample regression line. Sorry. And here you have the coefficients, right? And the coefficients you can observe because you calculate them based on the OLS method, the regression method we use. And so what you could do is you could just think of a certain portion of the data of the x's, and you could look at, is my line representing the average y, okay? So given a certain x, is my line representing the data, and you can see that the dotted line, it's really overshooting the data, whereas the solid line, it's in the middle of the data. I'm going to remove this, and you just do this for several segments, right? And you look at, does the line fit the average, or give you the average of y given the level in x? And what you see here is that the solid line actually gives you a better representation of the average y given x. So we would choose the solid line as our sample regression line. Okay, but when you do a regression, you have 5 assumptions, and these are assumptions of the relationship in the population of x and y. So these are not observed, okay? So remember that. So the first one is that the conditional mean for y, or y given x, is linear, okay? This is just the of y given x, or given the value of x, okay? So this dash here just means given, okay? And here you have a line, okay? The formula for a line, or equation for a line. So and this mu of y given x, the mean of y given x, is the same as the expectation, okay? So this is just the expectation. Of y given a value of x. Okay? So if you know the value of x, then you can get the average of the value y. So it's just our best guess. So an example of the average of y given x equals 200 would just be to take the intercept plus the slope times 200. And then you would get a value. And the second assumption is the expected value of the population error is 0. Okay? So these epsilons, these are population parameter. Okay? And if you have the population parameters of beta 0 and beta 1, then on average you would hit, okay, in the middle of the how to say it, you would get the average of y. So these random errors, they are centered at 0. So you miss equally likely at the upside or the downside. Okay. So these epsilons, they are random errors around the conditional mean, right? And the last three assumptions is that the errors are independent. Okay, and what does that mean? It means that sorry, if you know one error, you can't make a rule such that you can make an expectation or a prediction of another error. Okay, so for example, the correlation between error I and error J should be 0. Okay, so you should not be able to forecast the error in any way. And the fourth assumption is that the errors are normally distributed, and which means that if you gather enough errors, you can make, for example, a histogram which would get this, or approximately this shape. Okay, and they would be centered at 0. So this would be a count. And the last assumption is that all errors have the same variance. They are kind of drawn from the same normal random population, so to speak. Which means that if you plot the errors along the x-axis, then you should not, for example, this is 0, then you should have a stable, like a random pattern. Okay, it should not like be a funnel which increases Okay, so the variance of epsilon, or the error, should not increase or decrease when you plot it against the x. Okay, and here we have like a visual representation of this. So this line, this is the population regression line. Okay, the population regression line. So then you have beta naught plus beta 1, the intercept and the slope, times x. So this would be x, and this would be y. And you see that no matter which value of x you would choose, you would get the mean prediction given the population line equals the mean prediction and around this prediction you would have all these errors, or you would have an error which is caused by all the other factors besides x that affect the outcome y. Okay, because you would never make you would never be able to make a perfect model, okay, where all your dependent or independent variables can make a perfect prediction of y, because then you would need no statistics. Then you would have like just an equation and that's it. Okay, so what you can't observe would be the population parameters, and those you have here, and what you can observe is from the sample, and from the sample you get some estimates. Those would be the coefficients, and which means that this is what we want to know anything about. Okay, so these unobserved values or variables or parameters, we want to know something about them. Okay, but what we can calculate based on the sample, are the coefficients, which are just estimates of the population parameters. Okay, so because we never know the true relationship between x and y, we can use what we can observe. Okay, so we never know that the assumption of linearity is correct, but after we have gotten the sample, we can check our data to see whether or not a linear pattern or the regression assumptions might be true, okay, or might hold. So, for example, you can look at condition 1 and look for linearity in x and y, and you can just plot or scatter plot x versus y, or y versus x, and look for a pattern or a linear pattern. If you discover non-linearity, then you can make a transformation of one or both of the variables and try to make the relationship linear. Okay, so you can use the regression model, the linear regression model. Okay, and in addition, there should be no obvious lurking variable or confounding variable, which means that there should be no other obvious x variable in addition to the x variable that you have chosen to include in your model. And the residuals, they should be independent, which means that you can visually check your residuals versus the x. You can just like make a plot of the observed residuals, right? Oh, should not be I here. Your observed residuals versus the x, and they should be centered at 0, but if you find a pattern, then there is something that you have missed in your model and you have to check it. Maybe you have to include a different x variable in addition to the one you have. And the residuals of the or the variance of the residual should be equal. Okay. So which means that you should really have this quite random and quite stable relationship of the errors, okay, the residuals, when you plot them. And the residual should have a normal distribution, and this is actually quite important, because if you make a prediction, you are given or you have the model which is estimated based on a sample, then you're given a new x variable and you're asked to predict the y given that x variable. Then if you want to make a prediction interval, then if the residuals are normally distributed, then you can make like a prediction interval, okay, a prediction interval based on the fact that the error is normally distributed, okay, and you know all about the normal distribution, so you can just go approximately 2 standard deviations below your estimate and 2 standard deviations above your estimate, and you would be about 95% certain that your prediction or the true prediction would be inside that interval. Okay, and to check that the residuals have a nearly normal distribution, you could just make a histogram of the errors. Okay, and our example for today is Bucket-Hansen, and here you have done the regression oh, that's, you have done the regression, okay? And your output would be the slope, the B1, and the intercept B0. Okay. So from this output, you get the slope and the intercept, and then you know that the line, it's positive. So for every increase in x, you get an increase in y, okay, by 23, which is the sales, okay, and the intercept is negative, which really doesn't make any sense, but we'll get back to that. We'll get back to that. What's important for now is just to check whether or not our sample, these dots would be our sample points, and this y-axis would have the sales, and we are drawing this regression line with a positive slope. This would be delta y, and this would be delta x, and the slope would be delta y divided by the change of x, okay, change of y based on change of x, and in order to check the linearity of this relationship, we could plot the residuals against the x, right? Because the number of people walking by last month in thousands is the x, and then you see that the average of these residuals, they are centered around 0, which is good because they should, and we see that they have no apparent pattern. They look quite random, and they seem to be drawn from a distribution which have constant variance, no matter what the x variable would be. Okay, so and what you also would do is to make a histogram of the residuals, and here you can see that it's quite close to normal distribution with this peak in the middle, and they are centered around 0, and this would be the distribution from which your error is drawn. So if you make a prediction, then what you can't predict is drawn from this distribution, right? And what's interesting is that from the output of the regression, you get the root MSE, which is just the standard deviation of the error, or not regression. Like this number 150 is the standard error, or the standard deviation of the error residuals. Okay, which means that you have the standard deviation of the residuals, and you can use that here because this would be negative 100, and this would be negative 150, and you know that if you have a normal distribution and you go about 2 standard deviations below the distribution and 2 standard deviations above the mean of the distribution, then you can capture about 95% of the instances, which means that if you go to 2 times the standard standard deviation of the errors and below the mean of 0, and 2 times the standard error above your guess, then you can capture 95% of the instances. Okay, so you know that if you make a guess based on your regression line, then you can actually say with a 95% certainty that your the true y should be between minus 300 and plus 300 band around that guess. Okay, and in the next video we are going to look further into the Bucket-Hansen exercise.